In the third item, what we're trying to do is use this stress strain curve to figure out a couple of different things about what happens when this bar is first loaded up and then unloaded. Note that it has been loaded up and then unloaded so that it has a net strain of 0.004 millimeters per millimeter. We're trying to find the maximum stress that the bar experienced during this process and then the force that caused it to yield in its initial loading. Two different kinds of things. The bar is 2 meters long. It has a cross-section that is 3 millimeters by 8 millimeters. So this first part, the maximum stress that the bar experienced, we're sitting here and it has a maximum, or rather not a maximum, it has a net strain left over of 0.004. So when we are looking at this nonlinear situation, it's going to come up and then unload. It's going to unload and reload on the same slope as what the divergent curve was, that linear elastic region. So we could try to quantify it, but all we're really going to do here is draw a parallel line. And one easier way to do that is to extend this line and see where it crosses at a nice convenient number such as 0.002. And then we can draw a straight line across. That's going to turn out to be kind of useful for a variety of construction purposes. But note that that gives us a rise of, or rather, the constant rise over a run of 0.002. So when we come to 0.004 and we come out to 0.006, then now we know how to get a really good quality straight line going. Right? And where that line, which is now at this same slope as the original, where that intersects our stress strain curve, that was where this material was taken to. And so that's our sigma max. And depending on your interpretation of how to read that, mine was that we were approximately at about 2/3 of 80. Right, so this is 320, that's a 400, that's an 80, that's about 2/3. It might be about 3/4, but about 2/3 of 80 in that increment plus the 400 that we're starting with right at that little hash mark, and that will give us about 453. We certainly don't want to pretend like we're that precise. So right around then as an answer, 450 megapascals. So that's part A. Part B asks us to find out what the total axial force was at first, or initial yield. That means when we first come up this curve. Now, remember that the straight line portion ends at some point, and that would be our proportional limit, but that is not the yield. When we have a non-definite curve here, then what we have to do is go look at sigma yield associated with the 0.002 strain. And that doesn't mean going straight up there. It means we're going to do the same thing that we just did here, a line that is parallel to the initial curve, and we're going to come across, oh, we'll do this the same way we did this other one. We've got how much to come up at a delta of 0.002, so we'll just come along here and once again draw a line, and that will give us then our approximate value for our yield stress when we use the 0.002 offset approach. And there again, if you look, and by my eye that's about maybe a quarter, you might argue that it's a third of that increment of 80 from that minor hash mark to the major one. It is by eye. When you get a scale out, you can get a little bit closer to that. So I'm going to assume it's about a quarter, and that will give me a stress that's about 425 megapascals for the yield. Now, that's just the yield stress. We of course need to do what's been asked of us, and that's to get the axial force, which will just be then the stress times the area. And so we're at yield, so that's 425 megapascals, and then times our 3 millimeters by 8 millimeters. So that will be 24 times 425. That's 10,200. Of course, we got to figure out what the units are here. That's megapascals, which is the same thing, remember, as newtons per square millimeter. And so then times the millimeters squared. I'll write that out here. Remember that that is the same thing. And so with that in mind, then this is the same thing as 10.2 kilonewtons. And it's even a little goofy to report it to 10.2 kilonewtons. It's really, everything's so doggone approximate by the graphical reading here that that's about 10 kilonewtons for an answer.